Well, good morning, everyone, and welcome to the Fiber Broadband Association's Fiber for Breakfast. We're now in our 26th episode of 2026, so we're officially halfway through the year. Yesterday in Washington, Assistant Secretary Roth testified at a House oversight hearing that policy guidance for the over $20 billion in BEAD non-deployment funding, NTI is proceeding cautiously, so whatever that means. So hopefully we'll see some policy guidance this summer. And all but California and Illinois have approved BEAD final proposals, and 52 of the 54 states have signed their grant agreements with NTI and can draw funding. So, BEAD is well underway. At the FCC, the Fiber Broadband Association is engaged in a number of proceedings on poll attachments, public notice. The initial comments are due July 13th, in a couple weeks. For the 2026 Communications Marketplace Report, we submitted our reply comments, and we cited that fiber deployment continues to expand consumer choice, drive investment, and strengthen competition across broadband markets. We also highlighted that AI is changing the nature of network traffic, and the FCC should consider this dramatic shift going forward. For the high cost notice proposed rulemaking, we will actively participate as the Commission evaluates what a sustainable long-term framework would look like, and those initial comments are due on August 4th. And with respect to Section 253, the focus is on whether states and local practices are creating obstacles to broadband deployment through lengthy permitting and authorization delays, excessive fees, in-kind contribution requirements, and other considerations that might effectively prohibit broadband deployment. Those comments are due on August 10th, and replies are due on September 24th. So we'll be highly engaged in all those proceedings. And then we are preparing for our 4th annual Fiber Day in the Hill and DC Fly-In on July 15th and 16th. We'll be back in the Rayburn building on Capitol Hill, and we'll expect to meet with over 200 members of Congress, their staff, members of administration, and key agencies such as the FCC, NTI, and USDA, to name a few. So, we hope that we'll see you there on July 15th and 16th in Washington. And then our next regional workshop will be held in Bozeman, Montana on Tuesday, July 21st, which they happen to have a quantum computer over there at the university. So registration for Bozeman is well ahead of record pace. So if you haven't registered, please do so. You can do that on our website. After Bozeman, we'll be in Omaha in August, Boston in September, Savannah in October, Vancouver, British Columbia in November, and then we'll finish here with our premier member meeting in Islamorada, Florida in December. Last week on Fiber for Breakfast, our guest was Robin Olds from Cisco, who discussed building AI-ready networks, the next evolution of broadband. And Robin provided his insight on how AI is changing the role of the network itself, creating demands that broadband networks weren't originally designed to support. So if you missed last week's session, you can go to our website and watch the replay. Today on Fiber for Breakfast, our guest is Dr. Prem Kumar, the professor of information technology at Northwestern University. And he's going to discuss the quantum edge, why fiber providers should pay attention now. Dr. Kumar is a professor of information technology at the McCormick School of Engineering at Northwestern. His research focuses on quantum photonic devices and their applications in quantum information networks. He's a fellow of Optica, APS, IEEE, IOP, I guess I'm saying all these right, AAAS, and I'm not even sure what this one is. SPIE, SPIE. So any 4-letter acronym, Dr. Kumar is a fellow of. And he also spent from 2013 to 17 at DARPA, where he created and managed a portfolio of programs in basic and applied science. And then from 2020 to 2025, he served as editor-in-chief of Optical, the flagship journal of the Optical Publishing Group. He currently co-chairs the U.S. National Academy's Committee on Atomic, Molecular, and Optical Physics. So with all that, welcome, Dr. Kumar. And for our audience, please type in your questions as we go, and we'll work those in the discussion. So with that, I will turn it over to Dr. Kumar.
Well, thank you, Gary. This is an honor and a privilege to speak before your audience here. And I want to talk about why fiber providers should pay attention now in the quantum space. And I'm going to start by, of course, you've acknowledged the work is being done at Northwestern University. We have an Institute for Quantum Information Science and Engineering. Also, we're members of the Chicago Quantum Exchange. So let me move to the next slide here and talk a little bit about the ubiquitous connectivity that we enjoy today. The fact that we are hosting this webinar is a testament to that. And this didn't happen overnight. And people like Vince Cerf, Bob Kahn, these are what we call internet evangelists today. They were thinking about interconnecting small scale computers back in the late 60s and early 70s because they had a vision that if we provide connectivity, what might happen? At the time, of course, the early was file transfer email, but today even a 2-year-old takes email for granted. So it was important to set up these small scale networks because there were protocols needed to be like TCP/IP, transmission control protocol, internet protocol. Even today we use that. And ARPANET, of course, kicked it off, and NSFNet. There was a whole bunch of churn that took place. It was important to know where the demands were, what type of devices we should research on, what type of fiber connectivity as it came along. And today we live in this world of big data, AI, and ubiquitous connectivity through primarily a lot of it through fiber and, of course, other technologies as well. So computation and communication, it is so ubiquitous, we take it for granted in our hand all the time, 24/7, 365. Now, if we think about it, what is happening in the quantum space, there is something similar like the bit revolution I talked about is happening in what we can easily call qubit revolution. And that is primarily driven by advances in quantum computing. It all started out in the early 2000s. And of course, the theoretical progress was even before that. But in the last decade or so, the advances in quantum computing are so much that people talk about quantum computers being, omnipresent at universities, academic research labs, and so forth. But if you look at the roadmaps of advances in quantum computing, you find that every vendor who's developing every type of technology that's being developed, it is asking for modularity. That is, you would build out these units at scale, but you would need to interconnect them. So, in the same way as happened in the bit revolution, in the qubit revolution, I think we need to pay attention to interconnectivity, which necessarily in this case would be quantum interconnectivity between various nodes. And how those nodes would be scaled, that remains to be seen. So it is important to ask the questions like, how would a quantum network scale, for example? How would we build it? How would we control it, manage it? And all these questions we need to ask today. And so in that respect, it is important also to note that we can't build a new infrastructure that is dedicated to quantum because that is going to be very, very expensive. Otherwise, quantum signals, if they flow on dedicated fiber, we'll have to just parallel a huge network infrastructure in parallel. So it is important that we understand how classical and quantum signals can coexist in this scenario at the bottom, where fiber infrastructure connecting various sites can carry both quantum and classical signals. And that is where the frontier of research, at least my group and a whole bunch of others are exploring as to can we coexist quantum signals alongside classical signals? And I'll give you a few examples, and the answer is yes. So if we go to the next slide, so here's an example of an experiment that we did last summer in collaboration with companies like Sienna, Quantum Opus, NuCrypt, and a whole bunch of others, where we showed that you can send quantum entanglement from my lab in Evanston, Illinois, to downtown Chicago. So this is a roughly 25 kilometer link. And we distributed not only timing signals, classical signals, as well as quantum entanglement. So shown here on the next slide at a very high level is that Sienna helped us populate the whole C-band. This fiber at the time was capable of, even though we were only propagating 2 channels of 800 gigabits per second, but the whole C-band was populated with light. In principle, it is capable of over 20 terabits per second of actual data. On the other hand, same fiber, if you look in the O band, which is unused for usual classical communications, and by understanding how light scattering occurs in fibers, we showed that you can park quantum channels in the O band here, so somewhere in this region, and you can actually do entanglement distribution, and that is the work that we published on this archive just a few months ago. It's on the archive currently. And not only that, a couple of years ago, we did an experiment. We showed this is the same fiber, but in this case, spools of fibers in the lab, 2 spools of fibers. We showed that you can coexist even more advanced protocols like teleportation. This is quantum teleportation, disembodied in transmission of quantum information, where you first do entanglement distribution and then follow it up with classical communication, and then you port quantum information from one site to another. We showed that it was also possible to do that over 30 kilometers of fiber while the same kind of classical traffic was on the same fibers. Okay, so these 2 demonstrations, again, so this paper that we published in December of 24 was downloaded 20,000 times in 10 days. Okay, so there's a lot of interest in understanding how classical and quantum can coexist together. And looking forward, what we imagine is that down the road, this is a scenario, we will have networks where quantum and classical information will coexist seamlessly. There'll be datagrams, because quantum information cannot be directly measured, because quantum information, you measure it collapses, but we can create quantum wrapper datagrams. So this is the protocol that we have proposed with a colleague of mine at UC Davis, where classical bits of information, the same technology I just talked about, will precede or shepherd quantum payloads alongside, and then all the routing, network management control will be done by measuring these classical bits, and the quantum bits will follow along. And of course, to implement this kind of a scenario, we've done some rudimentary experiments, and I'll mention that in a minute. But we need to leverage advances in fibers, because to quantum signals, losses in the fibers is detrimental. So the emergence of new types of fibers, like people talk about hollow core fibers, and I'll have a slide on this in a minute. New developments in fibers like that, and rolling that out for networking, both classical and quantum together, is where I see the future being, which will allow people to seamlessly connect quantum resources and then follow. So here's an example of the experiment, the same fiber, but here we're creating these datagrams. So these datagrams are created here, and as they flow through this network, and then we measure them, and we show that you can shepherd quantum signals by making measurements on those classical headers that are part of the datagram. So this kind of a technology, I think, is going to play a role. If we can build out new types of fibers, which will allow us to scale further. Right now, that 25-kilometer limit that I talked about in the fiber connectivity that we have, maybe we can do 50 kilometers. But beyond that, we're going to require these new types of fibers, which have much lower loss. And the emergence of these new hollow core fibers, in which basically light propagates, even though it's guided by glass outside, but it really propagates in air. And those type of fibers are already showing that you can go way below the 0.2 dB per kilometer limit of standard fibers. So here in a paper recently, it was shown that 0.1 dB per kilometer of fiber loss. But I've seen conjectures and predictions where this number can be much lower. Even people talk about maybe 0.02 dB per kilometer. So if these kinds of fibers can be rolled out, I think the future of quantum and classical is very bright. And so in my lab, we recently, for this Optics and Photonics News, this is a magazine of Optica, the Optical Society, we wrote a cover article, how do we build out this quantum infrastructure? And a couple of my students here in the photographs, and if you, this is accessible open access, and we can see what kind of coexistence scenarios allow us to interconnect not only classical high-speed communications, but also quantum communications for networking applications and for perhaps security in the near term and distributed quantum computing in the long term. And so to summarize it all, I would say that, as you noted, Gary, that traditional data communication demands are rising exponentially, and the data salvo is generative and AI. Basically, AI is driving that. Also, there's tremendous progress happening in quantum computing in the last decade, and the build out of the quantum networks going to require quantum connectivity via optical fiber. And the new quantum-only infrastructure will be too costly to build. And recent work that I alluded to at a very high level shows that quantum classical coexistence provides a cost-effective path forward. And of course, the new types of fibers that are emerging, particularly hollow core fiber and multi-core fibers, they are quantum friendly from the beginning. And then, of course, AI is also going to help us drive the quantum, and eventually quantum will help even understand how AI works. And then that's one reason that terrestrial quantum connectivity is going to be very important. And the fiber providers which are providing traditional connectivity should also be looking forward to this future where perhaps we will have quantum computers solving hard problems of the day. So I'm going to stop here and take questions. I think my next slide is questions and discussion.
All right, well, Dr. Kumar, this is great information and just kind of really interesting on the breakthroughs. So in Chattanooga, EPB and IonQ have like the first commercial quantum network, because EPB's been kind of was the original gigabit community, and you've had fiber for decades now.
Right.
How pervasive do you see quantum networking across the country and the world?
I think it is pervasive in the sense that there are real bottlenecks currently in terms of distance. So I see that these new hollow core fibers is going to drive that progress. Currently, of course, there are a lot of companies trying to create these new types of fibers. Of course, because in those fibers, light propagates in air, so it is faster than in traditional fibers. So currently, the demand in the context of data centers is driving their development, and also exhausting whatever capability or whatever capacity one has. So at the moment, they are going in that direction. But I imagine in a few years down the road, those fibers would also be building out or replacing the conventional infrastructure. And once that happens, then the quantum signals and classical coexistence that I talked about would also scale the distance. So currently, I think in the near term, you mentioned Chattanooga, there are lots of networks. I described to you one that we have in the Chicago area. There are networks like that in the metropolitan New York, in Manhattan. And then there are many other places where quantum connectivity via fiber networks is being explored. So right now, the limit is the loss. And of course, fundamentally, that is the limit. And then novel fiber types like the hollow core fibers do point a path forward. And I would say that I don't see any fundamental limits in the sense that the physics says this cannot be done. It's a question of demand, it's a question of engineering, and the engineering community is clever, and they would rise to the challenge if it comes to that we need quantum interconnectivity between quantum machines to scale them. They will rise to the challenge.
Well, certainly. So we have a ton of questions that have come in for our audience. So I'll start with, do you expect the emergence of quantum memory and repeaters to change the options for designing long-haul entanglement networks?
That's a very good question. I think, to me, the hollow core fibers is a better scenario. Quantum memories are still very nascent, and quantum repeaters are even more nascent. I think, yes, down the road, again, the argument being the same that the fundamental physics doesn't rule them out, but they are very challenging to engineer and make practical. Not to say that progress is not happening, and perhaps there will be a lot of significant progress driven by AI, but the scenario of interconnecting quantum through hollow core is a much nearer term, relatively speaking, than quantum memories and repeaters.
Another question came in is it possible to have the classic and quantum channel in closer wavelength bands, like within C-band itself, or even within the 100 gigahertz or 50 gigahertz spacing? Is there any constraints?
Yeah, I think that's a very good question. The issue is scattering in the fibers, which we have explored.
Yeah.
So we have this one. I didn't go into the
You like mean
details.
dispersion?
Actually, so dispersion is an issue, but I don't think dispersion is the real limit. It's the scattering, so Raman scattering particularly,
Okay.
and Fove mixing nonlinearities, but predominantly Raman scattering. So in that one example of the experiment that I mentioned, our channels were about 3 nanometers apart, so about 3 ITU channels, and for distances we have, the scattering processes are manageable by making sure that you use good filtering as well as time gating. But if you want to do longer distance and in the network scenario where the signals are hopping over one segment to another, it is a scenario that can be managed, but one would have to design it properly. So we found, for example, backward Raman scattering, again, being rally scattered backward again, and the signals coming in where the quantum payload is. So these kind of things would have to be engineered. For long haul or for longer distance applications and high data rates, I think C-band, O-band scenario is better. But certainly for short haul or very short segments, perhaps the C-band might be a possibility, but one would have to manage the scattering processes properly.
So when I talked to Duncan Earl, and he was kind of sharing with me that qubits don't require as much bandwidth as you would see classical traffic. Is that not true?
So it depends on what type of qubits you're talking about, right? So the qubit is nothing more than, in the case of photonic signals. So when I talk here qubit, I mean a photonic qubit. From a quantum perspective, the bandwidth of a photonic qubit can be anything that you want, right? So it's a question of, so you can make photons very narrow band, and hence they would have the time duration would be very long, or you can check whatever you want. So currently, using techniques like in our experiments, are single photons, which are our photonic qubits, and pair of photons that are entangled in their polarization. They have bandwidths of on the order of a nanometer or even a half a nanometer. So that limits their temporal extent. So we have, and then of course, this dispersion, as you mentioned, is an issue that needs to be taken into account in that case, because 1 nanometer or half a nanometer is significantly broad.
So in the
So
past, when
all
I've
of these
looked at
can be engineered, yeah.
so when I've looked at quantum repeaters, it looked like one of the Achilles' heel was supercooling, and to try to slow down the entanglement. Um, but I've also seen studies that shown, or I guess announcements, press releases that have said that there's some quantum computers that don't have to be super cooled. What are you guys doing with quantum repeaters, and what activity at Northwestern on repeaters?
So at Northwestern, most of our efforts are photonic. So of course, there are many different platforms for quantum computing that people talk about. There is the superconducting platform, which requires cooling to like 10 millikelvin temperature. These are transmon type qubits on superconducting substrates. Then, of course, there is all photonic computing, which is like PsiQuantum building a huge mega factory in Chicago. And their protocols are all photonic. And then, of course, there are other modalities like IonQ that you mentioned. So those use trapped ions and they become qubits. And similarly, there are neutral atoms, which are also room temperature technologies, just like trapped ion is. And photonic, of course, is room temperature. So the question in terms of the work we have, the work at Northwestern, we're focusing on all photonic systems. One of my colleagues does experiments in solid state materials to build quantum memories that would work at room temperature. And so our focus, at least in our neck of the woods, is on that. Although we have collaborations with Fermilab, for example, where there's a lot of work. There is a superconducting center there funded by DOE, and they are advancing technology of superconducting quantum computation. But that's work at Fermilab.
So, I mentioned that my favorite quantum physicist, Michio Kaku, he was at our conference a couple weeks ago, and so he was on stage with IonQ, and so Dr. Kaku's kind of saying, quantum is, sometime in the future, and IonQ's like, well, no, we're kind of doing it right now. So one of the questions is, all right, when's your best guess on when quantum networking will be really commercially viable?
I think I would, if I were to bet, I would say 5 to 10 years. So if you look at IonQ as an example, again, I'm just an observer as far as IonQ is concerned, but they acquired several companies doing photonic communication, and then the LightSync is another company that interfaces photonic signals with matter qubits. Or ion-based qubits, and then they also acquired many cryptography companies. So I think the quantum future is here. The security applications are here. Distributed quantum computing is farther out, but certainly in the near term, as quantum computers scale, the applications they will serve would be early on in the scientific domain, perhaps drug discovery, better design of battery materials, and material science kind of things. So as you want to scale, then you would have to interconnect those quantum computers, and that's where the fiber connectivity is going to be needed. It depends on, but let's look at the standard data center, for example, right? A data center is millions of small-scale classical computers, whether they are GPUs, CPUs, or what have you. They are interconnected by very high-speed communications, right? So interconnectivity between compute nodes, classical or quantum, does not have to be long distance. So early on, perhaps quantum networks are going to be short-distance networks to scale quantum computing. Once we have the devices and infrastructure which can support longer distance for quantum signals, and that would come. And I think at this point, I would say 5 to 10 years is not too far away.
Well, it certainly seems like we have this perfect storm between quantum and AI as it keeps building on each other, and seems like
Exactly.
everything's accelerating at a faster and faster pace. So
That's right. Yeah,
I,
I
I
think in
think,
the near term, quantum, the AI is going to drive quantum. Actually, a lot of, I mean, the DOE has this Genesis mission that you may have heard about. So a lot of scientific progress will be driven by advances in AI. And at some point, then the role will reverse. And again, it's hard to predict, but at the pace of technology, it may be sooner than we think. Perhaps 10 years from now, it'll be quantum technologies driving understanding of AI. The role would reverse.
well, I think they're definitely building on each other. And we have a million questions that we can't get to, so I hate that we're not able to get all those. But Dr. Kumar, thank you so much for sharing what you're doing at Northwestern, and this is super exciting.
Wonderful.
I just think we're in an incredibly exciting time in our industry, and I appreciate you spending time with us. And I want everybody look forward to joining us next week. We're going to get back together with Ahmed Ali he's the optical and cable service expert for CRU Group going to share his latest research on optical fiber and cable market outlook, the role of hollow core and multi-core fiber. So again, that's the two topics that will continue to come up. But thanks again, Dr. Kumar, and look forward to seeing everybody next week.
Thank you very much. It was a pleasure.